A wastewater lift station begins with a simple visual problem. Liquid is rising in a wet well, while the receiving point lies somewhere beyond the reach of gravity. The station's job is to collect incoming sewage, hold it within a controlled operating range, and lift it through discharge piping and a force main to the downstream system. But the engineering decision is not simply choose a pump that moves the flow. The right pump is the one that can perform across the required hydraulic envelope while handling the wastewater, fitting the controls and power system, remaining maintainable, and preserving the station's ability to respond when something fails. That is why the station should be viewed as both a hydraulic machine and a risk control system. Influent arrives through the gravity sewer and enters the wet well. A pump and motor draw from that storage volume. Discharge piping, valves, and the force main carry the flow onward. Level measurement, controls, alarms, electrical supply, and emergency arrangements determine how the equipment behaves as the wet well level changes. EPA identifies the wet well, pumps, piping and valves, motors, power supply, and equipment controls as key elements of a pump station, and describes liquid level control as a common way to actuate pumps as the wet well level changes. The exact arrangement, however, belongs to the project design rather than to a generic diagram. The first engineering question is the flow envelope. Flow is not one universal number. The design basis may distinguish minimum, average, peak, initial, and ultimate conditions, but those labels must be defined from project data and adopted criteria. Initial and ultimate conditions may represent different stages of development. They are not values that can be invented for a fictional station. A defensible selection begins with the source of each condition: measured records, approved projections, infiltration and inflow assumptions, or another documented basis. A municipal owner guideline, for example, calls for initial and ultimate flow calculations as part of pump sizing. That is an owner-specific requirement, not proof that every jurisdiction uses the same categories. The flow envelope then becomes a capacity question. If one pump is unavailable, can the remaining arrangement manage the adopted peak flow requirement? Under a cited Texas rule, a lift station must have at least 2 pumps, and firm pumping capacity must handle peak flow. Those statements establish a regulatory example, but peak flow still has to be defined by the governing design basis. Other owners may add requirements such as 2 identical pumps, each sized for the full station capacity, emergency power, or 100% redundancy. A Western Municipal Water District guideline contains such an arrangement for its own facilities. The selection record should therefore separate minimum regulation, owner standard, and risk-based enhancement rather than blending them into one universal rule. Once the flow cases are identified, the next question is total dynamic head. How much energy must the pump add at each relevant flow? Begin with the static elevation difference between the upstream liquid surface and the downstream discharge condition. Then account for distributed friction in the pipe and force main, plus losses through fittings and valves. Conceptually, the system curve adds static head, friction loss that changes with flow, and minor losses through fittings and valves. Here, flow is the moving volume. Static head is the static elevation difference. Friction represents distributed pipe losses, and minor losses represent fittings, valves, and other local losses. The equation is a framework, not a license to insert unsupported roughness, efficiency, or friction values. The calculation should identify the pipe material and the friction method. The cited Texas rule specifically points to Hydraulic Institute standards for losses through pipes, valves, and fittings, and requires the friction coefficient used in head loss calculations to be identified and based on pipe material. Total dynamic head can shift as operating conditions shift. Wet well level changes alter elevation areas. Flow changes alter friction and minor losses. The force main condition can create different normal and peak system curves where the applicable design requirements are clear. For that reason, engineers compare. Finally, the pump's certified performance must be compared with those system requirements. The operating point is the intersection of the manufacturer's pump curve and the system curve for the stated configuration. Texas rules explicitly require pump selection from system head and pump capacity curves, and require checking the capacity and pressure head requirements for one pump alone and for pumps operating together. Parallel pumps must be evaluated as a combined performance arrangement. Heads are not simply added. The result is a transparent starting point. Define the flow envelope, build the system head cases, and then test whether the proposed pump configuration reaches the required operating points without hiding the assumptions that created them. A pump curve is only half of the hydraulic story. The other half is the system curve, the head the station requires as flow changes. Conceptually, the system curve adds static head, friction loss along the force main, and minor losses through valves, fittings, and other local effects. The symbols matter because the actual values belong to the project record, not to a generic example. The operating point is where the manufacturer's pump curve intersects the system curve for a defined configuration. Move the water levels, change the force main condition, open or close a valve, or change the number of pumps operating, and that intersection can move. A station therefore needs more than one nominal point on a graph. The designer should examine the applicable combinations of inflow, static elevation, friction, fittings, discharge conditions, and pump arrangement. The cited Texas rule explicitly requires pump selection from system head and pump capacity curves, including the capacity and pressure head requirements for one pump alone and for pumps operating together. That requirement also changes how parallel pumps are represented. Their combined performance should come from the manufacturer's or engineer's combined pump analysis. Heads are not simply added. The system curve must then be checked again against the combined performance. A graph may show a one-pump operating point, a multiple-pump operating point, and possible off-design regions. None of those points should be declared acceptable merely because the curve crosses the graph. Motor loading, efficiency region, control behavior, and the intended duty must all be reviewed against the project basis. A municipal owner guideline similarly calls for initial and ultimate flow calculations and system and pump curves for sizing, followed by pump and system curve testing before acceptance. The system curve itself must be traceable. Under cited Texas provisions, pipe head loss calculations are to use Hydraulic Institute standards for losses through pipes, valves, and fittings, and the friction coefficient must be identified and based on the pipe material. In specified circumstances, the engineering report must include normal and peak system curves at applicable force main friction coefficients. That is a jurisdiction-specific requirement, not a universal instruction for every lift station. The broader design principle is universal in practice. Record the method, material basis, units, and operating cases so another engineer can reproduce the decision. Then comes a different kind of hydraulic constraint, what the wastewater carries. Raw wastewater can include rags, wipes, hair, grit, and other fibrous or abrasive material. Clog resistance and solids passage are therefore selection constraints, not details to be added after the duty point is chosen. The cited Texas rule explicitly requires raw wastewater pumps, except for its specified grinder pump exception, to prevent clogging. It also requires passage of a sphere at least 2.5 inches in diameter, and suction and discharge openings greater than 3 inches. These numbers should appear on screen only with their Texas label. A Western Municipal Water District guideline gives a different owner-specific example. Non-clog submersible pumps, a minimum 4-inch discharge, and 2-inch sphere passage capability. The difference is the lesson. Do not merge values from separate authorities into a universal specification. The pump type, non-clog, grinder, vortex, or another free passage arrangement, must be matched to the solids, maintenance strategy, and adopted standard. A grinder does not automatically eliminate every blockage risk, and a brochure alone does not prove compliance. The review should require the applicable standard, certified performance information, materials compatibility, and a clear solids passage statement.
Finally, pump selection is a reliability decision. The cited Texas rule requires at least 2 pumps and firm pumping capacity for peak flow, with peak flow defined by the adopted design basis. A Western guideline is more specific for its own service context. 2 identical pumps, each sized for 100% of station capacity, together with emergency power and 100% redundancy. That is an owner standard, not a global rule. The design record should distinguish regulatory minimums, owner requirements, and risk-based enhancements. Ask the practical question. If one unit is unavailable, can the remaining arrangement manage the defined peak condition? Then test the answer with power loss, blockage, controls failure, and downstream constraints included. Redundancy reduces risk only when the surviving equipment, controls, power, and discharge path work together. The final selection is not the pump with the most impressive curve. It is the reproducible decision that connects hydraulic cases, solids behavior, firm capacity, and failure consequences to evidence. Now the pump has a hydraulic duty point. The next question is whether the station can continue to behave safely when the duty point moves, a sensor disagrees, a rag bundle arrives, or one part of the system is unavailable. Controls, maintenance, and risk review turn a pump selection from a curve-matching exercise into an operable facility. Liquid level control is a common way to actuate pumps as the wet well level changes, but level control is not yet a control narrative. The design record should state what starts the lead pump, what stops it, when a lag pump is called, and how the lead designation alternates so that service is shared. It should also describe the response to high level and high level, power failure, communications loss, sensor disagreement, and a selector left in manual mode. The exact elevations, delays, deadbands, and cycling limits belong to the project basis. They are not generic values to be copied from another station. A robust sequence begins with a normal operating band. As the level rises through the project-defined start threshold, the lead pump runs. If the level continues to rise, the lag pump is staged according to the approved logic. When the level falls, the pumps stop under the corresponding stop condition, with anti-short cycle behavior verified against the wet well volume and inflow pattern. Alternation can be scheduled by runtime, starts, or another owner-approved method. The important point is not a particular sequence. It is that every transition has an identified purpose, an alarm path, and a safe response when its expected feedback is missing. The high-level alarm is a warning to an operator. The high condition should initiate the project's emergency response, which may include dispatch, bypass planning, emergency power, or other measures defined by the owner and regulator. A redundant float, independent alarm path, or fallback state may improve resilience, but it does not automatically guarantee that an overflow cannot occur. The review must ask what happens if the primary transmitter freezes, the float is fouled, the pump fails to start, the check valve leaks, or the force main cannot accept the expected discharge. Maintainability begins before the first maintenance call. For a submersible pump, the cited Texas rule requires a rail-type support system that permits removal or replacement without personnel entering the wet well or dewatering it. The rule also addresses movement and vibration during operation. The practical review therefore follows the entire removal path: guide rails, lifting chain, access opening, lifting capacity, laydown area, isolation, check valve arrangement, blockage removal, washdown, and safe work boundaries. The design should make the intended intervention visible on a drawing, not merely promise that the pump is serviceable. Owner guidance provides a useful example of the documentation expected around that intervention: manuals, records, operator training, factory testing, and pump and system curve testing before acceptance. These are owner-specific requirements, not universal law, but they illustrate a broader principle. A station is easier to operate when the approved curve, motor and controls data, spare parts list, as-built drawings, PLC files, alarm matrix, and maintenance history remain connected to the equipment actually installed. Lifecycle cost and maintainability belong in the decision record alongside purchase price. Now build the risk register without inventing probabilities. List blockage, power loss, level sensor failure, reverse flow, force main air, corrosion, odor, flooding, and unsafe access. For each hazard, record the consequence, the detection method, the barrier, the responsible owner, and the evidence that the barrier was tested. Separate 3 layers of decision: what the adopted regulation requires, what the owner standard proposed, and what a site-specific risk assessment adds. Texas, for example, requires at least 2 pumps and firm pumping capacity for peak flow under the cited rule. A Western Municipal Water District guideline gives a different owner-specific example involving 2 identical pumps, each sized for 100% of station capacity, emergency power, and redundancy. Neither source should be presented as a universal arrangement.
The symbolic selection is now complete. The datasheet contains the defined flow envelope, static head, friction loss that changes with flow, minor losses, the solids and debris requirement, the operating modes, the redundancy question, and the control narrative. The conceptual system curve adds static head, friction loss, and minor loss. The selected manufacturer curve is checked for 1 pump and multiple pump cases, certified performance, motor compatibility, solids passage, removal method, alarms, testing, and acceptance. No invented flow, head, efficiency, motor rating, alarm level,
or emergency storage duration is needed. The final review question is simple. Can another engineer reproduce the decision from the sources, assumptions, curves, tests, and approvals? If the answer is no, the pump is not yet selected. It is only proposed. A defensible lift station decision is not the largest pump, the cheapest pump, or the most familiar pump. It is the pump and control system whose performance, failure response, maintenance path, and jurisdictional basis are all visible, traceable, and reviewable.